Alright folks, we are back with our chapter 19 notes. You'll have a little bit of textbook homework to do after this, so I'm going to try to make it as quick as possible, but also hopefully without crazy information for you. Okay, so confidence intervals, very similar to what we did with confidence intervals for proportions, but this is going to be for means. One thing I want to point out is that you get a t-score. This you actually want to get from your graphing calculator, or technically if you end up taking a college course, they have tables for it. It's based off of something called the degrees of freedom, which is n-1, literally your sample minus 1. The reason they do that is because sometimes in a sample you end up with like one piece of information that's messed up in some way, so this kind of takes care of any error that might pop up. So you're going to take your mean, which is usually given to you. You multiply your t-score, very similar to a z-value, and then you times that by your standard error. Your standard error is going to be your standard deviation, s over the square root of n. The difference here is that that's your sample standard deviation, so it's different than standard deviation from a population. The nice thing is that for 95% confidence, the rule of 2 still works. So what we're used to using for that is going to be the same, which is nice. Okay, so we're going to go through an example. You are going to need your graphing calculator. So I'm going to write down the steps, but if you ever need to join a meet, feel free to do that for my next office hours. Okay. So notice that they're actually giving you a lot of the information in this question. They give you your mean, okay? They give you your standard deviation. Now it says, what does your 95% confidence say about your data? So your degrees of freedom in this case would be 49 because it's 150 minus 1. You have to plug in your standard error formula, so it's your standard deviation, over the square root of your sample size. So you end up with 0.0040. This number, just so you know, probably looks really similar to a z-score that we get for a normal model with 2 standard deviations. But what you're going to do to get this is go to second distribution. Okay, so click on the second button. There is a distribution button, which is basically vars, aka vars. Hopefully you're enjoying the meditation music I have going on behind me. If you need a minute, just pause the video, take some breaths. We never got our mindfulness in this week, so I've been doing a little bit of yoga occasionally, which helps. Anywho, second distribution, vars. You want to go to what says inverse t. On mine, it's number 4. Okay, what you're going to see is either area, degrees of freedom, and then paste, or you'll just have parentheses. If you just have the parentheses, just type in the numbers and put a comma in between. Our area is going to be 0.025. The reason that works is if you look at the normal model, if we're doing a 95% confidence level, when you're looking at 2 standard deviations on either side, this adds up to 5%. What does one of these add to? That's right, 0.025 or 2.5%. So that's why we're going to use that area. The nice thing is you only need the lower half because that literally just gives you the t-score for one of them, which is really all you need, which is kind of nice. Our degrees of freedom we already found was 149. So again, if you have the older calc, you're just putting these numbers here and here. So if you type in 149, then if you hit paste, or for most of us that's just enter, you get a t-score of negative 1.976, which is the same thing on the other side, just positive, so 1.976. Technically, because we're adding or subtracting that same number, it doesn't matter that it was negative or positive. You can change it to a positive if you want for the positive. So notice they take that number and they multiply it by your standard error, add it and subtract it from the original Y bar, which is the mean, and you get your confidence interval. So you can say you're 95% confident that the mean level, notice they're saying mean, not proportion anymore, of Murex concentration in farm-raised salmon is between these two numbers. So hopefully it feels really similar to what we did with proportions, but now it's just means, so you have to use a slightly different process. If you need me to show you on my screen what the calculator buttons look like for this, please join my office hours. If for some reason you can't at the time I post, just email me and I'll find a time to meet with you. All right, so the directions here I think are pretty self-explanatory, but I will go through them. This is if you're given data. So what you want to do is enter in your two sets of data into L1. These are all the same data. They just like break it up into two rows, which is weird. So this all goes into L1, just so you know. This, and then also this. So it's like one big list of data, okay? Once you have that in your stat edit, if you forgot how to get there, stat edit, it's been a little while. You want to actually graph it and see how normal it looks. Remember, we have some conditions that if we have a certain amount of data, we want to make sure it looks fairly normal. This is a small amount of data, so we want to make sure that we actually check the graph first to meet that normal condition. So it says, looks okay, fairly unimodal and symmetric, so we're good to go. Then you're going to go to stat tests and go to number 8, which is interval. You want to make sure data is highlighted because that's different than if you enter a statistic, which we're going to do next. You want your list to come from L1. So notice that's literally what's highlighted here. Okay, your confidence level is always going to be 95% unless they tell you otherwise. And then it literally, once you hit enter, gives you all of the interval, it gives you the mean, it gives you your standard deviation, and it gives you the sample size. So you can see whether it fits in that interval or not, which is kind of nice for the nearly normal condition. So hopefully that went okay. I like their little heads up about what should we say. We're used to this, so just make sure you recognize you're saying 95% confident because you're not 100% confident. This data. So if you somehow erased it, that's the data you need in L1. All right, a little bit more calculator stuff here. So this is the same, it's actually the same button in your calculator, but it's if you're not given a list of data. So say you're given statistics instead. They say that the sample lengths of 53 fishing lines, so this would be your N is 53. They also said that suppose the mean strength is 83 pounds, so that would be your Y bar, or if you're looking at your calculator, they call it X bar. And then your standard deviation, which we call S, but your calculator calls it SX, is literally 4. Okay, so that's what you would enter in for those values. So if you forgot where to go, it's the same button as the last problem, but you would just go to stat tests, number 8, which is T interval, but make sure you're toggled over to stats instead. Once you're entering all that information, again, they give you your interval for you. So you don't have to do a whole lot, which is kind of nice. All right, so number 2, I know I'm running through, but I just don't want to make these notes too long. Number 2 is very similar to what you just did, so I'm going to have you try it out. Make sure that you are using the correct option on T interval. In this case, they're not giving you data, they're just giving you values or stats. So choose that one. So pause the video, try this out for me. Make sure you actually check the assumption based off of what we think this is going to look like, especially with the fact that we have 24 batteries to choose from. Find your confidence interval and then interpret that confidence interval for me, and I'll have it done for you in a second. All right, hopefully you assumed that the graph of this would be approximately normally distributed. We can't see the data, so we have to assume that it's going to be normally distributed. Your confidence interval, again, you can just go to your stat test Number 8 is exactly like what we just did. Put in the numbers. So 24 was your N, 47 hours was your mean, and then your standard deviation was 3. And then check out their interpretation of the confidence interval. I'm not going to read it to you because you can read. Scoot back. Oops. It was... Okay, so hypothesis for means. So they're kind of combining everything at once in this chapter for means. Again, you guys did this in chapter 18, so hopefully it feels pretty familiar. You'll see that they give us a lot of the information in here again, where you're figuring out a t value very similar to a z-score. Even the formula is almost exactly the same, except they're using means. So notice again that the y bar would be for your sample. Mu naught would be the mean. This is the mean for your sample. The mean for mu is the mean for your null hypothesis, which again they'll give you. And then SE is still your standard error, like before. So, really important pieces of information when you're doing a hypothesis test. The first thing you need is, oh yes, hypotheses. That would be helpful. Figure out your test. So in most cases, ours is going to be a t-test. Number 3 is going to be mechanics. Okay, so that's like the math, you know, like what they show up here. And then your conclusion. Oh, that is a terrible way to write conclusion, but hopefully you can see that okay. So we're going to go through a full example of that right now. Again, make sure you have your graphing calculator handy because that's going to help us get through some of these together. All right, so our first example, they really like these farm-raised fish. They tend to use the same examples over and over again. The way that you figure out what your alternate hypothesis is going to be, because your null is always going to be that mu equals the original average, your mean. But they said, as a safety recommendation to recreational fishers, they recommended screening values for 0.08 parts per million. So that's your first. Our farmed salmon contaminated level beyond the level permitted by the APA. AKA, are they greater, sorry, that was poor English. Are they beyond the level permitted? So that tells us that we have to be greater than. Again, check out how they used the standard error here. Again, their t-score they did by hand. You would want to do this one by hand just to verify things. Especially because you're using that as mu, so just be careful. Now you have a formula here, and that's 2.796. Think of that as like a z-score, if that helps you to think about how that looks as well. Notice it's a little bit more than 2.5 standard deviations, or t-scores with this model, away from that mu. So notice they used mu as the center. The other thing is, if you didn't get from the last chapter how to find your p-value, I want to remind you of that. So it says using technology. Well, what do you mean? So if you have a t-score of greater than that, what you want to do is go into your graphing calculator, like we usually do. Okay, so you're going to go to second distribution again, which is the same thing as we were doing before. But this time you want to go to t-CDF. Notice it's really similar to what we're used to with normal CDF, except this is a t-model. Slightly different formula when you're talking about means. If you're talking about proportions, that's when we use the normal CDF. Excuse me. So in those little options, you're going to have a spot to put your lower bound. Your lower bound in this case is going to be that t-score, right? Because we want to shade to the right. So you're going to go from lower being 2.796. Your upper, as we're used to doing, is just 99. And then they also want your degrees of freedom. So again, if you have the older calculator, in between all these, you're putting commas. So it would be TCDF, this number, which comes from here, comma, 99, comma, your degrees of freedom, which, if you look at the problem, was 149. So that actually gives you your probability of this happening. So this is kind of a two-check step. Somebody had asked before why we need to check both. The t-score is greater than 2, so we reject our null hypothesis. But also, checking the probability of it happening, because it's so low, if it's less than 0.05, it's just an extra confirmation that we're rejecting our null hypothesis, which basically means that if you were to interpret it, the Murex level is going to be greater than 0.08. So they actually say it does not exceed the APA screening level, but it does. They misspoke in this question. So because we're rejecting our null hypothesis, it actually is greater than 0.08. All right, the next one I want you to try, see if you can work through the directions on your own. They're pretty self-explanatory, but again, you have to do you have to do a t-test for data again if you're going to use that same data you had. So it says, hopefully you still have that data in your L1. I think you should, unless you somehow paused and deleted everything. But in L1, you should have the data from the last problem still. If you need to look at it. Okay, so you're going to store that data, go to stat test number 2 again, but this time you're choosing a t-test because we're actually doing a hypothesis test. You want to have data selected. Your mean here is going to be 30 because that's what they used in the last problem. Make sure you highlight the correct inequality statement, meaning they're saying that for your alternate hypothesis, we want it to be greater than, because in this case, we want an upper tail test, very similar to this problem that we just did. Once you hit enter, you should get all of your information. The nice thing is including your p-value, so including your probability. Notice that this is 0.126. It also says T and P differ slightly from the values we worked out in our examples, because when we did it by hand, we rounded. So notice in both of these cases, remember we don't say reject, we say fail to reject, which means our null hypothesis was probably true, okay? So that's why you have to be careful. They kind of go through 2 problems in one here, where they say, if you didn't have data, you do the same thing, except you just entered into stats. So you would just toggle over if they just gave you values. You don't have to run through this one if you don't want to, but notice the p-value. Just so you know, if you ever get conflicting p, like probability, and t values, your p-value always supersedes. So your p-value is always going to take precedent, because every once in a while they get a little bit close to each other. But say you're between the two, excuse me, your probability always wins, which is nice. Okay, so this problem was in your reading guide, so I'm not even going to really go through it because you did it already and the answers were in your textbook. If for some reason you don't have your textbook, because I didn't post the link to the textbook this time, just let me know and I'll send you the link to it. But you had the answers to this from your reading guide, so hopefully you're good on that question. Okay, this is the last really new thing that is going to be important, is something called a paired data. So paired data literally just means you have data that's over the course of different scenarios. Okay, so it's the same kind of data, you're looking at the same thing, but for example, this day is different from that day. So you have 5-day mileage versus 4-day mileage. What you always want to do with paired data is figure out the difference between the data first. So literally just subtract the numbers. Usually they'll tell you which one's first and which one's second, but this would be like your L1 and your L2. And then if you remember how to put stuff in your L3, literally on the top of L3 it would be L1 minus L2, and it would do it for you. But we're going to run through that in a sec. Just a reminder about why these are paired data. It's because each driver's mileage is measured before and after the change in schedule. So some kind of condition is changing, but it's all the same kind of information, okay? So notice a lot of these formulas have D in it now, because if we looked at our paired data, we found the difference. Notice that it's always going to be 0 for your null hypothesis, because you want to see as a null, nothing has changed. There's literally no difference between the two values. So it'd be like on day 1, I have 1, 2. Day 2, I'd have 1, 2 again. So if you think that there's no difference between them, the subtraction between these two values should be 0. Okay, your t value, the same idea. What's nice about this formula is you're subtracting 0, so you really only need the mean of your differences. So all these formulas are really the same, which is why I'm kind of doing them quickly. Notice same formula, but now you're with differences. Like I said before, if you ever need to enter in data and you're looking for D, aka the differences, what you could do is highlight L3, take L1 minus L2, and it'll literally do the subtraction for you. They have another way to do it in here, which is totally fine if you want to use their way to do it. But one thing to be careful of is when you're checking the nearly normal condition, you want to make sure you're graphing your differences. So you actually would be graphing L3 here. So quick reminder of that in your calculator is if you go to stat plot, so second y equals, if you hit enter and you have your data on, just make sure that if you're trying to graph a normal model, that you're trying to graph the histogram, so toggle over to histogram, and then make sure L3 is listed in there, because you really, with paired data, that's the only big difference, is you want to actually graph L3 to see if it fits the nearly normal condition. They also gave you a nice window. I know I'm running through this really fast, but if you want to try it, you're welcome to. If you trust me, fine. You're going to have to do it at some point. But if you need that practice for yourself, please work the data out and then make sure you check it afterwards. Okay, got 2 more things to look at. Just a reminder, paired data, very similar to what you just did, but you need to check assumptions and conditions like we always have. Just it's called something slightly different because it's paired data, so they call it the paired data assumption. Pretty much the same thing. Independence assumption, randomization, and nearly normal are exactly the same as they were. Okay, so make sure you check those for just hypotheses. And then a reminder that if you're doing a hypothesis test for paired data, just a reminder that your data is coming from L3. So that's the big difference. The other thing to notice is that your alternate is most likely going to be that they're not equal to each other. So it's almost like you're saying your data from the first does not equal the data from the second. You could also just say that U1 minus U2 is greater than 0 or less than 0, depending on the question. But a lot of times it's going to be that they are just literally like not equal to each other. So hopefully that makes sense, because if they're not equal, then there's a difference between them. Okay, we're going to run through the last bit here, which is an example of this. Okay, so the example they're giving you is doing a paired test. So remember, the difference between your data, you want to say is 0. That means that there's no change, okay? Most of the time it's going to be not equal 0 for your alternate, because that means that there's some kind of difference between them. These calculations, all the same that we've already done, so just run through them quickly by yourself, but you don't have to do them all out. But notice, one thing I want to point out on here is if you have something where it's not equal 0, it's called a two-tailed test. Because if it's not equal to 0, it means it could be either greater than or less than. So also a reminder, because this is less than 0.05, you would reject your null hypothesis, which means, I want you to check out their conclusion, that the change in the work week did lead to a change in the average driving mileage. So you can't say that one is higher than the other. You could just say that they are different from one day to the next. Okay. Again, confidence intervals for paired data, same exact thing. Just keep in mind if you're doing paired data that you have to use L3 for your confidence interval, okay? Feel free to read through the confidence interval problem at the bottom, but just a reminder that these are all the same things. They just call them paired data if you have data that changes from like one day to the next, or they do, for example, I could do the difference between like you guys and the other class, the other stats class, something like that. Anyway, I wanted to keep these as short as possible. Please join me during my office hours if you have questions. I hope you have a great rest of your day.